Hello, everybody. We're going to be presenting our senior project, Rugged Internet of Things Microcloud. The developing team on this project was 3 software engineers, including myself, Antonio Leonti. We also had the Scrum Master, Alexander Thibedeau, and Ikenna Chibueze. We also had 2 mechanical engineers on the project, John McGovern and Eric Santos. Our client for the project was General Dynamics Mission Systems, and our correspondents were Gianni Sanchez and Daniel Matheson. So let's hop right into it. UAVs typically have multiple devices collecting data at all times, and if it's piloted by a human, it's kind of the job of the human to interpret that data and tell the drone what to do from it. But if the drone is operating autonomously, that burden falls onto some computing system. So there are multiple ways to do this. You can use cloud computing, which basically means you send all of the data that you collect to some remote server, and that remote server takes care of processing the data and telling the drone what to do. But that introduces latency, because you have to wait for the message to send and then receive your message. And it also requires bandwidth, because you need to send the data, so you need a network connection. It doesn't work very well like in the middle of the ocean. So what we're going to do instead is called edge computing, which is, it basically entails we're going to connect a computer to a UAV directly, and that computer will take care of the data processing, allowing the UAV to run mission control software without latency or needed bandwidth. These kinds of systems already exist, but they're orders of magnitude more expensive than what we've made. So the way we've reduced cost is by using off-the-shelf parts, open source software wherever possible, and whenever we can't buy something online or in a store, we just use the most cost-effective techniques to manufacture it. So to get more specific into what we've done, we have 3 single-board computers. They're all communicating with each other through an Ethernet switch. Those computers will be running a K3S Kubernetes cluster. And on top of that, we also have other software infrastructure. And the idea is, on top of all that, the end user mission control software will use that infrastructure to perform its mission control tasks. All of that will be encased in a rugged enclosure, which will perform 2 functions. One is to keep the internal safe, and the other is to provide a hardware mounting interface so that it can be attached directly to the UAV. So the rest of the presentation will just elaborate on these things. We'll go over the computing hardware that we chose, our Kubernetes configuration, the additional software infrastructure that we configured, and our mechanical engineer's enclosure design. So we're going to start with the hardware selection. First, the requirements, then the Ethernet switch that we chose, the single-board computers that we're using, and our hardware accelerator that we chose additionally. So on the right, you can see how everything will be connected together, or is connected together. So there's 3 single-board computers. They're powered by some black box external power source. They communicate through an Ethernet switch, and one of the boards is designated to power the Ethernet switch as well through USB-C. So all of these pieces have to be off-the-shelf parts. They also need an x86 instruction set architecture, and each board needs 1 terabyte SSD space and at least 1 hardware accelerator on board. So our Ethernet switch is pretty simple. It's just a Ubiquiti Flex Mini. It's a small managed switch. You just plug stuff into it. It works. It can be powered via USB-C, and it's pretty small and also pretty light. Our single-board computers are Neo 2375s. They come with 32 gigs of RAM on board, so we don't need to buy additional RAM or anything. They also have Intel i7 processors, and those have integrated graphics as well. And like the switch, they are also small and pretty light. They're actually a little smaller than the switch. Now, the integrated graphics actually covers the 1+ hardware accelerator requirement for each of the boards. However, our client described that our end user will most likely need to do some machine learning inference tasks. So we got a hardware accelerator specifically for that. It's this Coral TPU. It plugs into one of the M.2 slots on our boards that we have free. And we ordered it. It's on back order right now. Supply chain issues were kind of the bane of the project. But we've also documented how the client can integrate this into what we've done already. So it should be pretty easy for them once they get it. Now I'm going to hand it off to Alex to describe our Kubernetes configuration.
Thank you, Antonio. Hi, my name is Alex Thibedeau, and I'm going to cover the next portion of this demonstration. So in this, we're going to cover the Kubernetes intro, the benefits, requirements, and as well as our configuration. So what is Kubernetes? Kubernetes is a container orchestration software system. Each container provides a OS-level virtualization. It allows us to manage the life cycles of our containerized applications with the provisioning, deployment, and scaling. It also has a client-server architecture, meaning there are many remote processes sending and receiving requests from a centralized server, or the master node in this instance. It also has a publicly open design. So there are many benefits to using Kubernetes, but the ones we're going to cover are the abstract host hardware. Normally with a cluster like this, you would need to know which server you're interacting with, but with Kubernetes, we're able to interact with multiple servers through a single interface. It also has built-in common deployment patterns to help with time saving and reusability. One of the more common patterns, the one we use, is the daemon set. This allowed us to replicate pods across multiple nodes. It is also self-healing, meaning a containerized application, if it was to go down, Kubernetes would recognize this and redeploy it to its desired state. It also has inter-process communication, and this allows the processes to communicate with each other and synchronize their actions. So for our configuration, we chose a simple bare metal K3 setup with one master node and two worker nodes. The master node is acting as the interface for our developers. So in the next section, I'll be covering the CI/CD pipeline, the NFS server, device plugins, benchmarking, and Portainer. So CI/CD, or continuous integration, continuous deployment, is our automation suite that helps us to integrate our source code, test it, and deploy it. It is declarative, meaning when a developer specifies a desired state, the configuration management tool determines the best way to achieve this. It also supports our other infrastructure, our software infrastructure, to include our NFS server and our hardware plugins. So here, as you can see, is an overview of our CI/CD pipeline. Whenever the developer is pushing changes to our K3s manifest repository or our source code repository, Jenkins is constantly monitoring for any changes that are being made. And when it finds a change, it will build the new image from the code and then update the version numbers. In doing so, it indirectly triggers Argo CD. And when Argo CD is triggered, it will take these changes and deploy them to our K3s cluster. So to help illustrate this, we put together a short demo. We have a simple Hello World program running on our source code repository, and we're just going to show what happens when we make a change to it and then push through the process. All right, as you can see here, this is our current output from our program. It's just a simple Hello demo. Now, this is the actual program we're running. We're going to make a quick change to it, so it's going to say Hello World. Now we're saving it. And then we're going to push these changes to the repository. Now we're switching over to Jenkins, and we're going to kind of force a build right now rather than waiting for it. Normally it would do this every 5 minutes, but for time's sake, we're just going to do it like this. And at this moment, it's already built the new image, and now it's currently testing the image. Once it's finished testing the image, it will push that image out to the repository, and then eventually it will update the version number, which will then trigger Argo CD. So we're just about finished with that, and we're going to switch back over. All right, so again, normally Argo CD would be automatically doing this, but for time's sake, we're just syncing it up right now. Now, since everything has worked correctly, we're going to load our current outputs, or the new output. I'm just going to say Hello World. So as you can see, the CI/CD pipeline is working as advertised, and I'm going to pass it on to Ike to handle the next portion of the demonstration.
So my name is Ike, and I'm just going to go over the rest of our software tools that we implemented in our cluster, starting with our NFS server. So as Antonio already mentioned, each of our boards have their own distinct storage, their own distinct SSD storage, and our end user software will be running on top of our cluster, which will be on top of all of our different nodes. Now, the end user software, the pods it runs may need access to the same storage, so that's where the NFS server comes in. Essentially what it does is that it allocates a specific volume of storage on any of the boards and makes that available for the cluster, enabling all of our end user software to read and write to the same storage. And to test this, we actually came up with just a simple daemon set. The way it works, as you can see, is that this pod runs on all of our nodes, and they just log a simple output to the same text file located on one of the nodes. And whenever we look at this text file and just see the logs, as long as all three of them are writing to it, that proves that our NFS server is correctly configured. And we actually have a short demo just to demonstrate that. So with the first button, it just shows the names of all of the daemon set pods that are running. All of them are active, shows what nodes they're on. And then with the second button, it shows the output, the last two lines of that text file. And as you can see, all the names match up, proving that the NFS server is correctly configured. All right, then moving along to our next software feature is our device plugins. Now, as our end user software won't be running directly on the boards or on the Kubernetes cluster, the cluster will need abstracted access to our hardware accelerators. That's where the device plugins come in. Essentially, the way they work is that they advertise the device drivers for the actual hardware to the cluster, making them available for use in the end user software. It was very easy to source these. Fortunately, we didn't have to write them ourselves. Intel already has a very in-depth repo for their various hardware for use in Kubernetes. And for the Coral TPU as well, we were able to source another repo just providing those device plugins. And these plugins are also very easy to test. All the repos come with a test pod that when you run it on your cluster, assuming it's able to run successfully, that proves that the device plugin has been correctly configured. And moving along, next we just have our benchmarking tools. So we use Capstone, which is just a suite of benchmarking tools, and in particular we use two of their tools, starting with SysBench, which essentially just allows us to benchmark our CPU and memory performance. And then in addition to that, we use FIO, which allows us to benchmark the read-write speed of our SSDs. And continuing along, finally we have Cortana. So as you can see on the left, typically with Kubernetes development, it's primarily terminal-based, which isn't exactly the prettiest thing to look at. So that's where Cortana comes in. As you can see on the right, it essentially just provides a prettier front end for server management, allowing you to check the status of your pods and your nodes, just to make sure everything is running and make some lightweight configuration changes. And then from here, I'm going to pass off to Eric to talk about the enclosure.
Thank you, Ike. Going forward, I'm going to be talking about the mechanical enclosure known as the Agile Pod Enclosure, designed by myself and John McGovern. We were the two mechanical engineers on the project, given to us by GDMS. Were specific specs and limitations that we had to go and design around going forward. Those spec limitations were primarily to do with volume and heat management, as well as keeping the internal safe from any type of external interference. That would mean that it would have to be a rugged, weatherproof solution, something quick, easily manufacturable, something that can be easily changed through any type of means necessary. Here is the full assembly of our design. It's exploded outwards. The red and green are the Agile Pod halves, and gray is the aluminum heat sinks. Yellow is the component divider, and in blue is the plexiglass covering. Here we have the external shell. Both are made within a female and male half. This split design was made because we had constraints within our 3D printing capabilities in-house to where we can only print out a maximum volume. So by cutting them into two shapes and then later on joining them together, we were able to end up with a final product that was much bigger than we were able to manufacture in-house. That being said, these two halves were made out of a thermoplastic ABS plastic, which was then joined together and repolymerized with an acetone solution. This acetone solution was put on the faces of the female half of the enclosure, and then they were press fit together, and a chemical bond was formed through the repolymerization of the plastics. Here we have the aluminum plates and heat sinks slotted into the female half of the enclosure. Like I said, the aluminum plates are held together by tight tolerances. They just slot together, and then the component divider, once that's in there, everything kind of just is in perfect fit with each other. This aluminum plate is what's providing heat management to the 3 CPU boards that our CIS colleagues have put into the project. Through conductive means, any type of heat energy or excess exergy that is latent within the system will dissipate towards the aluminum plates and then outwards towards the ABS plastic. I will now pass the torch off to John McGovern.
Thank you, Eric. Hello, ladies and gentlemen. My name is John McGovern, and I shall be presenting the final mechanical parts of this presentation, starting with the component divider as seen in yellow here. All the component divider really is just a 3D printed partition designed to hold, contain, and make sure that all of the electronic components are remaining in contact with the aluminum heatsink. It does this with a combination of tight tolerances and the interaction between the connecting cables and the lid, making a nice tight fit when all is assembled together. However, as you can most likely see, rather admittedly not as well as I would like on this rather small engineering drawing, there is a bit of a stage on one corner of it. This is because when we had gotten the 5-port Netgear switch in person, we had noticed that there was a power port on the bottom. In order to counter this, we created this stage. As such, we are capable of inserting all of our components with the Netgear switch residing on that stage with enough clearance for its power jack to remain connected, yet still have enough functionality. It would be kept in place with some form of holding. We decided on zip ties. It's really just interchangeable with anything that anyone feels is necessary. Those holes in the bottom is where those zip ties would lace in and keep it steady. Moving on, we have our plexiglass lid to keep everything finished up with a nice little bow. All it really is just a nice simple piece of plexiglass with a groove cut into the bottom face to allow for a rubber O-ring. This O-ring, once all the pieces are assembled together, is designed to create a waterproof and weatherproof seal to prevent any debris or water from getting in or out and thus ruining the components forever. And nobody wants that. Here we have the 3D design of what we had hoped for the entire assembly to look like. This is how the assembly looked when my colleague Eric and I had just assembled it together with the acetone solution. And this is the final result with all the components all assembled in together. And not to sound too smug, I think we all did quite well. A final note on the mechanical side of things. As I'm sure you may have noticed, there were bracket holders incorporated into the enclosure design. These bracket holders would then be screwed onto the drone's attachment plate as indicated by this helpful red arrow. Unfortunately, due to supply chain issues, we were not able to get the drone in-house, and through no fault of their own, our sponsor General Dynamics was unable to find any specifications for us to create something as accurate as we possibly could. We just put those in there for proof of concept as to show how it would connect all together. Just to wrap everything up, this project entailed the selection and programming of hardware and software, the design and manufacturing of a rugged enclosure to hold everything together, all with the goal of lowering costs as much as possible to allow for a higher production for our client company. And with that, I open the board to questions.
Hi, first of all, great project. I had a quick question about the enclosure design. I'm assuming that the final product is going to use 3D printing and most likely be
Yes, we did. The 3D printer that we had, one of the 3D printers that my partner Eric and I had access to, the maximum size that we were able to use was 10 inches cubed. So we had to create a design that was capable of holding all the components that were given to us or assigned to us by General Dynamics, create enough of an aerodynamic design that would allow it to function as we intended, while also being small enough to actually be manufacturable.
Got it, thank you.
Any further questions, please?
Seeing as that this is a like a cross major effort, I was kind of interested to see is what was the biggest challenge from both a software perspective and from a hardware perspective, just to see the differences of the development process.
So, as for the mechanical design portion, I would say the hardest aspect for us was to kind of see how the computer components were going to work together. I mean, we were supposed to have an ECE major as well on the project that was supposed to be like that bridge between CIS and M&E, but we didn't have that. So, luckily our CIS majors were able to get the boards working and get the connections running. The major difficulties was trying to figure out those connections though. How are we going to get the space management for these connections? These boards are a specific size, they have to lay in a specific way, they can't be rotated a certain way, they can't be jolting around. So basically just kind of designing around the electronic components for us as the mechanicals was the hardest part.
I didn't really know how to delegate before doing this project, so having people on the team that were doing things that I literally have no idea how to do kind of forced me to actually learn how to do team lead things instead of just doing everything I can.
You guys were awesome.
Thank you.
Hey guys, how's it going? Great project. I just had a couple quick questions, mainly in sort of the computer hardware and the mechanical component space. I was wondering if you had any sort of, if you had done any testing in terms of waterproofing. I know you said that you wanted to make this a weatherproof enclosure.
We have not done any testing per se, if only because of the time constraints, the fact that most of the components that we had needed had not come in. We had a bit of a supply chain issue with screws involved, and well, if I'm being brutally honest, the enclosure design itself only really finished printing about 3 days ago, and even then, we were still waiting for all the water to drain out from having to wash it from the solution to dissolve any of the scaffolding. It still drives me crazy because I received the final part Wednesday at 8 o'clock. It only finished draining 9 o'clock last night. So if you'll pardon me for being a bit salty about that fact. There's nothing I can really do about it. It's just how the way 3D printed material works. It just bugged me.
That's right, thank you. The other question I had was just in the realm of heat dissipation. I was wondering if if you were able to test that with the working hardware components on the computer side too.
So I was able to generate little tiny diagrams up in SolidWorks where I made tiny little square boxes. Unfortunately, in the presentation, we didn't have time to show my thermal testings of it, but I would create a tiny little thermal producing box and I'd place them inside the enclosures. I'd tell them generate this specific amount of heat, which was usually the maximum amount of heat generated by the board possible. And then I would see how much of that heat was traveling through the conduction plate of the aluminum sink and then the ABS plastic. At some points, there was points where we would possibly have to insert another heat spacer onto possibly one of the other CPUs. But other than that, the dissipation was flawless.
Awesome, that's really interesting. Thank you guys.
Also, one more thing on that, the power supply that we have doesn't fit inside of the enclosure, just because that's what we got to test the boards and set them up. So yeah, we can't actually do real life testing with that.
Thank you. Any other questions, please? Going once, going twice. I know it's time for lunch, so thank you, Antonio.